So last week we found out the average of a function, and we were on this slide talking about you already know how to find out average velocity and average speed. Because if you would do that in the past, you would just say, well, how far have I gone? What is my total displacement over a certain amount of time? That's just displacement over time. Here's your change in displacement. Here's your change in time. That's just a slope of a secant line. You found that before. But now we also have that we can find an average of a function with 1 over b minus a, and then finding the definite integral of that function. And it's kind of neat to see that with average velocity, if you do the integral of velocity, you get displacement function, and the definite integral means you plug in b, you'd subtract plugging in a, which would just be s of b minus s of a. And of course, that's divided by b minus a, so it's exactly the same thing. Now, if your question said average speed instead of average velocity, you have to be careful here because there is a difference between displacement and distance. So here you would need absolute values around your velocity function because negative parts of the graph that are below, where the displacement would be calculated as negative, is actually still a positive distance. And of course, average acceleration is just your velocity, change in velocity over change in time, which you could do also with the integral. Oh, great. So we've got a particle moving along the x-axis, and you have its velocity function. At time equals 5, is the particle moving to the left, or is it moving to the right? Well, if we plug in 5 into our velocity function, we get a velocity of 6. Since that velocity is positive, in this situation, it would tell us that it's moving to the right. A negative velocity would tell us that it's moving to the left. If we find the acceleration, which is the derivative of our velocity, we could plug in 5 into this, no problem. And we get an acceleration of 7. Recall, what does that mean from previous units? If the velocity was positive and the acceleration is positive, what did that tell us? That it's speeding up, right? It's getting faster. So if both the velocity and the acceleration are the same sign, then you know it's speeding up. If they're different signs, then you know your object is slowing down. So at time equals 5, our object is speeding up in the right direction. Given that x of t is the position of the particle at time t, and x of 0 equals 12, so this looks like a solving for C question. Well, we're going to solve this using our definite integral. We would know that the integral from 0 to 3, here's our integral, here's evaluated from 0 to 3. We could plug those numbers in. And we could calculate the actual value is negative 16.5. And since you know that this is also x of 3 minus x of 0, and you know that x of 0 is given to us to be negative 12, we could just plug this in and find out that x of 3 is negative 4.5. So this would be one way of solving for this. The other way of solving for this, and I'll do it in purple here, is you could have actually found out, just using the indefinite integral, that x of t as an equation would be t cubed over 3 minus 3t squared over 2 minus 4t plus c. And because we know that when time is 0, that it's 12, you'd be able to solve that c is equal to 12. So then you would get that x of t equals t cubed over 3 plus, minus 3t squared over 2 minus 4t plus 12. And you could just plug in 3 into that and solve for x of 3 that way as well. So now we get to see different ways of solving the same question. Different ways of solving the same question are valuable because if you're on an exam, you might say, which one is faster? Which do you like better if you didn't have a calculator? Are they about the same? Possibly. Okay? Usually the fastest method on an exam is the method you think of first. You should probably just go with that. Okay? But if you get to that idea of, I have two different ways I can solve a question, maybe one way of thinking is going to help you in another question more than a first way of thinking. So in this question, I could solve it like a solving for C question, get my equation, and then I just have to plug in 3. If you plug in 3 and solve it, sure enough, you get negative 4.5, just like before. But I could also use a definite integral and say, hey, if I'm doing my definite integral, I'm going to get x of 3 minus x of 0. And solving this, I get negative 16.5. Therefore, I can just plug things in to get my value. And then in D, find the total distance traveled by the particle from time equals 0 to time equals 6. Here we have to have our absolute values inside of that function. Thinking about the graph of that function, we have a parabola. It has from 0 to 6, the blue part would be considered negative. The green part would be positive. So when we do the absolute value, we're basically taking this lower section here and flipping it up so that we have all positive values. If this was a non-calculator question, you would have to break things up by going from 0 to 4 and then from 4 to 6. And because the 0 to 4 is negative, notice that instead of, I could have put absolute values. Sometimes students will do this, and I wrote a negative out in front because I knew that this answer would be negative, and I wanted to make it positive. So how do you make a negative answer positive? Multiply by a negative, okay? You could also show in your work here, if you wanted to not have that negative sign there, you could have put absolute value bars around that first part, because you know that that's the negative part, and we need to make it positive in the end anyways. So however you want to show that, that's fine. That's up to you, personal preference. But we know that that blue part is negative, and we need to make it positive. And I also know that integrating with an absolute value isn't something that we're very good at, if at all. So instead, we think about integrating normally without that absolute value. Plugging in our values, getting our answers. And we get 94 over 3. Now, for all of the assignments that we give you this year, we're going to ask you to write a final answer. Okay? If on your AP exam you had something like this, and you put a box around that answer, you would get full marks. They're not expecting you to simplify simple arithmetic stuff on the final exam. So that's, again, when we get closer to the exam, we'll talk about those kind of strategies. Because this takes time to plug things in and get an answer. So if you can save time by not having to do a bunch of arithmetic, that's going to be advantageous for you on your exam as well. So we're going to look at that again as we get closer to the exam. We talk about a few of these things now, but we'll give you hints for studying for your exam and what you need to do at that time as well. Okay, and then find the average speed of the particle, right? That's the distance traveled over the time. We figured out the distance traveled was 94 over 3. The time is 6. No need to do the more complicated average value function with the integral, because we've already done that. And then finally, for what values of t is the particle's instantaneous velocity the same as its average velocity? Okay, so now, instantaneous velocity, that's related to the derivative. The average velocity we already figured out, and that average velocity doesn't change. So basically what we're trying to do is we're trying to get our average velocity to be equal to our instantaneous velocity. So our average velocity, here's the formula we've already, right? This is different than average speed, so we don't use the answer from above. We're using average velocity. I'm using the integral right here. And we get an average velocity of -1. And we need that average velocity to be equal to our instantaneous velocity. So here's our velocity, our instantaneous velocity. We set it equal to 1. We get an equation, which is a quadratic equation. If this was calculator, you go to your calculator right away to find the x-intercepts. It's not calculator, then you're going to need your quadratic formula. This is jumping around, I'm sorry. And in your quadratic formula, So your instantaneous velocity, that's your actual velocity at a moment. You had a velocity equation. We take that velocity equation, made it equal to the average velocity. Quadratic formula, now something that you feel like you can whip off the top of your head? No, that's one you still gotta. This is the good thing about doing questions, right? When formulas come up in a question, now this is like, okay, if you didn't know the quadratic formula by heart, right? Write it down on your hand, that's your homework for tonight. It came up and you didn't know it. If you do nothing about that, guess what? The next time it comes up, you won't know it. If you want to know it, after something comes up that you don't know, that you needed, that's telling you should take some time, make sure I know my quadratic formula, because I just had a question where I needed it and it wasn't ready for me. Okay? If you study that way, if you study formulas when you need them, you'll remember them more than if you just go, okay, tonight I'm studying 50 formulas and trying to memorize them. It's going to be less helpful that way, rather than after each time that you needed a formula, you're like, okay, negative b plus or minus square root of b squared minus 4ac over 2a, that is going to be more helpful. All right, our last kinematics question for a while. A car is traveling on a straight road with a velocity of 80 feet per second. Is that fast or is that slow? I am not good at, as soon as you give me different units, like I know how fast I drive my car. Usually a little bit too fast, but I'm working on it. But if all of a sudden they came out with cars and just had, they're like, we're going to change it, we're no longer going to put kilometers per hour on your car, every car is going to come out with feet per second, I would be totally confused. Is 80 feet per second actually really fast for a car? Mediocre? Anybody know? For running, I think it's pretty quick. If I could go 80 feet in a second, I think I'd be a pretty fast runner. I think that'd be pretty good. What does it come out to?
80 feet is 24 meters, so it's 24 meters a second.
Okay.
That's like 90 kilometers an hour.
90 kilometers an hour. I would love to be able to run 90 kilometers an hour. I think that would definitely improve my soccer prospects for being drafted. Okay, so they've given, you have this graph. I've already split it up into a bunch of stuff. We want to find the acceleration at 15 and the velocity at 15. So if you are given a graph, the acceleration at 15, that's easy. You can just go to 15, get your point, and you get negative 20 feet per second squared. If we want to find the velocity at 15, velocity is moving backwards. That would be the integral of acceleration. The integral, if you're given a graph, the integral is your accumulation of change. It's the area under the curve. So if I go up to 15, which I'll label that purple line there so you can see it, what we need to do is we need to figure out what is all the areas under the curve up to that point. And we'll also need to have our initial velocity. So our initial velocity, we're starting at 80 feet per second, and then this is the accumulation of change. If we add the 100, the 50, and the negative 50, we can see that we have changed an extra 100. That 100, that accumulated change, gets added on to the 80 that you had originally. And so now the velocity at 15 seconds is 180 feet per second, more than double. So if the 80 was 90, now you're going really fast because we've more than doubled. I think that's what the person realized here. They were at 80, they added 100, now they're 180. They're going 230, and then they're like, wait a minute, I should probably slow down. And they actually slowed down 250 in this situation, which would mean they've decided to turn around and go the other direction for a bit. At what interval other than 0 is the velocity of the car 80 feet per second again? So again, if this is accumulation of change, we started at 80. This would mean you added 150. Can you see that when you get to this green line, you've subtracted 150 after adding the 150? So we can use the graph and say that it will be true at time 20. So from 0 to 35, we want to find the maximum velocity and the minimum velocity. And at what time do they occur? Okay, so if we're using accumulation, can you see that we're at 80, we went up to 230, now we're subtracting again. When we get to this point, we'd be at minus 20, and then we add 25 again. So based on that accumulation of change, starting off with 80, all of those positive accumulation of changes, that extra 150 that gets added on, you would get a maximum velocity of 230 feet per second. Then if we add all those negative accumulations of change, we get to negative 20 feet per second, which means somewhere in there, the velocity is 0, and the person is changing directions. Question asks, what time do these occur? Right? This one happens at 10, this one happens at 30. If we check the endpoint, you're only going 5 feet per second, so it's going really slow right at the endpoint. Just something to note in these equations that's maybe a little bit new that we haven't done before. You can always find a new velocity if you take something that you previously know, so this v of 30, we already figured that out. That's a previously known velocity that we know. And then from that point 30 to 35, that will be an accumulation of change added onto that. So the area under the curve shows you an accumulation of change that's happened from that point. So if I want to find V35 and I know V30, all I would have to do is add the area from 30 to 35, that'll be my accumulation of change, put that onto my initial value, and then I get my new value. So in this case, we'd already figured out that V of 30 was at negative 20. Then adding this last bit of area from 30 to 35, which we know is 25, means that negative 20, I added 25, that means my final velocity at the end of 35 seconds will be only 5 feet per second.